all cones have the same helper equation if they are going to be inverted, going to give us similar triangles. So pretty much if I were to take this cone right here and make a 2D picture of it, have my r over h is always equal to the form of 3 over 8, because our r is always 3 and our h is always 8. Hello everybody, welcome to our video here for Cranky Calculus. Here we talk about related rates. There's a lot of different types of related rates problems, so I'm going to go through which ones that we have, which ones we're going to do, but first I'm going to explain what a related rates problem is. It's a problem that asks how fast one quantity is changing based on another. So these are word problems which are scary for many people. So let's go ahead and tackle these things. And actually, before I do, there's three types that we're going to go over in our videos. There's geometry measurements. This is the video for the geometry measurements, but there are going to be other videos on the Pythagorean identities and angular rotation. Regardless of what type of problem it is, all these steps are the same. We're always going to draw a diagram. We're going to identify what's given, what we need, write an equation that relates to everything, identify a helper equation that helps us with these, and then we're going to do our calculus and derive implicitly, and then do substitution to find out what we need to know. So here we go for our first problem here with our geometric measurement related rates problems. We have a water tank in the shape of an inverted circular cone with a base of 3 meters, a height of 8 meters. If the water is being pumped into the tank at a rate of 4 meters cubed per minute, find the rate at which the water level is rising when the water is 2 meters deep. So first thing I'm going to do here is I'm going to draw myself a picture. Now an inverted circular cone is similar to an ice cream cone. So this matters a lot because what's going to end up happening here is water's going to get into this tank, and I'll kind of draw that right here. So the water's going to get into this tank, and that shape of that water matters a huge deal for when we get into that part with my need for the helper equation. So what I do know about this is that this is going to have a radius of 3 meters, and this is going to have a height of 8 meters. The cone itself, not necessarily the water. So with this picture, I'm going to go ahead and start to name everything that I need here. And actually, before I even do that, we're talking about volume, adding water into the cone. So we're going to say that the volume formula here is 1/3 pi r squared times h. That is our volume formula. So now, with what we're given here is we are given the dV dt. Since we're pumping water into the tank, we're going to be a positive 4. And what I'm trying to find here is I'm trying to find dH dt because it's when water is rising. So in my volume formula, it's going to relate to h. So I need dH dt. I don't know what that is, but I know I need that at h equals 2. So I want to find what's going on with our water at height equals 2. Now here's the deal. As we're pumping water in, the height level is going to change depending on how much water there is. So I can't just start plugging everything in. I first need to find the derivative. Now, I can totally find this derivative as is, which is going to involve product rule. It's going to spit out dr dt's, dh dt's, dv dt's. But the only problem is I don't have any dr dt. So I'm going to go ahead and use my helper equation. Now, all cones have the same helper equation if they are going to be inverted. What the equation is going to be is it's going to give us similar triangles. So pretty much if I were to take this cone right here and make a 2D picture of it. Okay, so here's my height, which I know is 8. My radius is right there. If I have the water level at somewhere like about here, that is going to give us similar triangles. So I'm going to have my r over h is always equal to the form of 3 over 8 because our r is always 3 and our h is always 8. So no matter what our height of our water is, it will be in that proportion of 3/8. So I'm going to use this to solve for r so that I can eliminate my r. So r is 3/8 h. So I'm going to come back and substitute that into my volume formula, which is going to make my calculus go so much easier. So volume is going to equal 1/3 pi 3/8 h, and that's all squared times h. If I were to solve for this a little bit further, I'm going to get 9 over 72 h squared times everything else. So that is going to actually help me reduce this down to 3 over 64 pi h cubed. Okay, so now I'm ready to differentiate. And I'll do that part right here in black. So I'm going to get dv dt equals, the derivative here is going to be the 3 over 64 pi stays, and the derivative of h cubed is going to be 3h squared, tag it with a dh dt. Now I will clean this up just a bit here. Let's make this dv dt equal 9 over 64 pi, h squared dh over dt. So now what I'm going to do is I'm going to use all my givens here and start to substitute in, and I actually kind of ran out of space here, so if you don't mind, I'm actually going to use this space right up in here, and I'm going to finish this all off and using my black right here. So I have my dv dt, which is 4, which is equal to my 9 over 64 pi times my h I'm using is 2, so 2 squared is indeed 4 dh dt. So what I'm going to end up getting here is I'm going to divide both sides by 4. Just doing this mentally real quick. I'm going to end up with 64 over 9 pi is my dh dt. Yeah, because I divide both sides by 4, and then I multiply by the reciprocal of 9 pi over 64, and I'm just going to get my dh dt that way. So what is this actually saying? That my dh dt is changing. I'm going to give you some units here. Is going to be 64 over 9 pi. Units here are going to be meters per minute, and this is kind of my final step right here, final answer right in here. If you want to estimate what that is, since pi is pretty close to 3, it's 64 over almost 27-ish. So that's going to give us a value that's a little bit over 2. And that's going to wrap up our very first problem. Moving on to here, our last problem here with some geometric related rates. We have a thin sheet of ice in the form of a circle. If the ice is melting in a way such that the area of the circle, area of the sheet is decreasing at a rate of 1/2 inches squared per minute, what is the rate of the radius decreasing when the circumference of that circle is 12 pi? So let's go ahead and draw our lovely picture here. So we just have a circle. Let's see here, what else we got? That's really it. We just got this circle that's melting. A couple of things that I do know about this is the area. So the area is changing, so dA over dt. If it says it's decreasing, it's going to give me a -1 over 2. And I want to know at what rate is the radius decreasing. So I want to know what dr dt is when the circumference is equal to 12 pi. So essentially what I want here is I should know the area of a circle is pi r squared. Now, I can't take the derivative quite yet because I don't really know what r is. Well, I could take the derivative, but that's not going to help me out so much where I'm at right now. I don't know what r is, but I can go ahead and use my lovely helper equation here. That helper equation here is I know the circumference is 2 pi r. And for this particular problem, we have 12 pi equals 2 pi r. So I have r equals 6. So now I feel a bit more comfortable taking the derivative of my area here, and I know I can substitute it in a 6. So I'm going to get dA over dt equals 2 pi r, tag this with a dr dt, and now I do have everything. So my dA dt is -1/2. My r is 6. When I plug that in, I'm going to get 12 pi times dr dt. When I divide that over, I'm going to get a final answer here. I'll write it in black. I'm going to get a final answer of, everybody think by 12 pi. I'm going to get dr dt to equal -1 over 24 pi, and we have, it looks like, inches per minute. And this is going to wrap up our first video with our related rates.